Namaskar and welcome back to another lecture in our course on Introduction to Infrastructure Asset Management. This is the third lecture in this module and we'll continue our discussion from the previous one where we talked about non-destructive testing and evaluation methods for concrete structures. This is basically a case study where concrete structures are being used as an example to show you some of the techniques that we use for their non-destructive testing and their evaluation. So moving forward, this is the statutory kind of slide which tells you that the material being used in this course is strictly for academic and instructional use in this course and should not be used for any other purpose. What you see on the screen is like the blackboard of the good old days, and please make it a habit to make notes using what is visually projected and what is orally stated. So continuing with our discussion from the previous class, where we basically talked about non-destructive testing of concrete, traditional methods. We talked about the Schmidt hammer, how it is used. We talked about the ultrasonic pulse velocity, and we talked about the pull-out and pull-off tests. Basically, methods by which we approach the concrete structure and try to find out what is the in situ strength. The strength that we get is for a local area. That's something which we must keep in mind. As far as our discussion today is concerned, we'll talk about the electromagnetic method in the reinforcement locator. We'll talk a little bit about the natural half-cell potential which is used for reinforcement corrosion. This is something which we will not talk about. The in situ examination using chain drags or delamination, that is something which we will not talk about, but we must remember that we did spend some time talking about the measurement of surface cracks using the crack gauge. Continuing on the methods that are used for non-destructive testing, the more recent developments, we'll talk a little bit today about infrared thermography. We'll talk about image processing. It looks very fancy, but what we will talk about is basically collecting images through normal cameras or any kind of a tool that you use and use that image for understanding what's going on in the surface. We will not talk about acoustic emission or impact echo, in situ permeability methods and dynamics-based structural health monitoring methods which could be active and passive in nature. You should also remember that we can talk about application of drones in data collection. We can talk about using embedded sensors for real-time data collection, but all this is subject matter for a full-fledged course on non-destructive testing and evaluation. That not being the objective as far as this discussion is concerned, we will leave it for another day, or you, at least those of you who are interested, can use these as pointers and do a self-study. So moving on, how do we use cameras? So basically, images provide an objective visual record involving changes on the surface in terms of changes such as appearance, discoloration, cracks, etc. So what we have is sunlight or some kind of an illuminating source falling upon the concrete surface, and this surface is captured using a camera. The advantage of the system is that depending on details such as the hardware used or the distance from the surface, different types of details can be collected. Also, it can be used to study the changes in the surface over time, so long as we are able to keep some parameters fixed. For example, the distance and so on. That helps in trying to study the changes at a particular location over a period of time. This method is something which can be very easily used in studying the changes on a road surface. Taking images today, taking images tomorrow, a year later, we can find out what are the kind of changes that are happening on the surface of the road. But we should remember that details only about the surface can be captured. We do not really know what is happening below the surface. What we can find out from cameras and images is only what is going on the surface. So with this limitation and perhaps an answer to that, we move on to infrared thermography. Now this is something which is based on the principle that radiation incident on the surface is reflected or absorbed. So this incident radiation is either reflected or it is absorbed. Now if it is absorbed, it's fine, but if there are voids or delaminations, some kind of defects within the surface, this absorbed reflection is reflected back from these surfaces. And what that leads to is higher temperatures on the surface. That is, this radiation which goes back heats up this surface here a little more than the surface here, where no radiation is being reflected back from within the concrete surface. So, this method is basically an external visual inspection method based on changes in the surface temperature arising out of issues or changes within the surface. Here are examples of what we will see at the surface for two cases. Now, these two cases are from laboratory studies, and this is what the laboratory study is. So, we have a concrete surface which looks pretty normal, very standard, very clean, but there are voids deliberately placed behind this apparently smooth surface. What those voids are? It could be in the shape of an A, and if you notice carefully, the depth that we have used is not necessarily uniform. So, if we take a thermograph of this at the top, this is what it will appear as. So, what it tells you is that this temperature is, let's say, 34.4 and this temperature is 28. So, on a scale like this, the absolute values don't really matter. What matters is that method tells you that there is something going on here which needs attention. That is, there is something here. Of course, in this case, it is planted, but it tells you from the surface that this area is a place which needs more careful examination. Instead of an A, if the block or the gap is in the form of an H. Now, this is the previous example where we have A, C and P, which is this hollow portion again being reflected in some changes here. So, there is a temperature here, this a temperature here, which is higher. So, that is basically the use of or application of infrared thermography. And you would recall that we had talked about tunnel surfaces and said that, okay, if there is a tunnel lining here and there were some pockets here, maybe the earth or something which has got trapped somewhere here, this will reflect in the changes in the temperature. So, if we map the temperature of this surface using infrared thermography, we will get a different temperature here, and that is indicative of some issue here at the back of the wall. So, moving forward, what we have done is methods such as the Schmidt hammer, the UPV, crack detection and so on, that require close access and yield specific information about a small neighborhood. But methods such as images, which could be normal or thermographic, give a more generic picture of the condition of the structure based on the surface condition and help us identify areas that need closer attention or examination. This aspect is something which, as managers, we must keep in mind, that if we want specific information, then we really need to go to smaller areas. We have methods available from technology point of view, which will give us a specific information about a small area. But in order to narrow down that small area, we need more generic, more robust tools which will help us scan the entire surface. And that's where methods such as infrared thermography will come in handy. Moving on, let's try to look at the electromagnetic method for rebar location. This is the principle here. This is a means of internal inspection in a sense, which involves the use of flux to estimate the location and at times the diameter of the reinforcement that is used within the concrete. And it's useful for core drilling, measurement of natural potentials, and at times finding out how much reinforcement is there within the concrete surface. What we see here is the reinforcement bar locator, and it is being used to get information about the reinforcement within this concrete surface. There are ways in which we can find out the depth of the reinforcement, the diameter at times, of the reinforcement and the location. So if we are mapping a concrete surface with reinforcement bars like this, and we move the reinforcement locator, we will find that, okay, here is the reinforcement, here is the reinforcement, and here is the reinforcement. We must keep in mind the fact that it's much easier to draw these diagrams, and if we see actual data coming out of machines, coming out of, for example, in this case, the rebar locator, it's not all that clear. But yes, it's good enough for engineers to be able to make a judgment as to where the reinforcement bars are. Moving on, we have the core cutting machine, which helps us in core extraction. But core extraction should be resorted to with utmost care, because in any concrete structure, no manager will allow indiscriminate extraction of concrete cores. Cores, of course, are an invaluable source, or can prove to be an invaluable source to provide information about different aspects, and they help us study the in situ concrete in terms of its strength, chemical composition, and so on. They provide a lot of information, but again, from a very local area. In a concrete structure, which is, let's say, a road, which on the surface looks like this, and if you look at it from the top, you could have a road which will have several lanes like this. So you can take cores if you want, and if it is allowed by the owners of the roads, only at specific locations. And the cores will give you a lot of information about that area. But it's very difficult to say that this information can be generalized over the entire kilometers upon kilometers of road which may have been built over a period of time. We have, of course, portable equipment to help us take cores from different places. We must keep in mind that reinforcement is not damaged during core extraction, and we must study the reinforcement layout, because it is very important to ensure that reinforcing bars are not damaged or cut while the core extraction is carried out. I am leaving it to you to find out more details about what information can actually be extracted from cores which are extracted from its structure and brought to the lab for further testing. Now, we've often talked about carbonation studies in concrete. Here is an example where a core was extracted from the wall here, and immediately phenolphthalein solution was sprayed. So we can see that this depth here is the depth of carbonation that can be observed. A similar thing under laboratory conditions is shown here. I would only like you to remember and note that this depth that we measure here, or for that matter in laboratory studies at different locations at different points in time using different concretes and so on, it's very difficult to come up with a single number x which will be the carbonation depth at a given point in time. When we had talked about carbonation in the previous module, we had said that as far as the design is concerned, as far as the management is concerned, we need to ensure that the carbonation depth x at service life should not exceed the cover provided. Now, the point is that if this depth that we measure at different points in time is so variable, then what should be the value of x that we take here? We can take the minimum value, we can take the maximum value, we can take an average value, and so on and so forth. So now that's something which we have briefly touched upon, and I'm reiterating again when we talked about estimating the remaining service life, or we had talked about how to use the data that is collected from carbonation studies to predict or to do mid-course correction as far as inspection of concrete structures is concerned. Moving on, this slide shows the method of measurement of natural potentials. Now, what is done here is that the reinforcing bar is exposed from within the reinforced concrete structure, and one terminal of a voltmeter is connected to this bar, and a copper sulfate electrode typically is connected to the other, and from the surface using this copper sulfate electrode we record what is called natural potentials. Now, measurement of natural potentials of reinforcement yields contours of equipotential lines. So basically, if we have a large concrete surface, we will get contour lines like this, let's say minus 250 millivolts, minus 400 millivolts, minus 500 millivolts with respect to copper sulfate electrode. Now, based on this kind of information, we can say that, okay, this is the area which is more likely to have corroded. The values could be affected by local conditions, for example, the kind of saturation that is going on here, the cover that we have and so on, and the method also requires access to the structure. So this is one of those methods again where specific information about an area can be obtained, but the point is whether we can carry out this investigation for an entire bridge deck or for an entire 2 kilometer or 3 kilometer section of a long highway. Depending on the kind of resources we commit, this is possible and we will get the information. I'm leaving it to you to study the relevant standards and find out the importance of these values. Similar to natural potentials, we have concrete resistivity measurement. You remember, concrete serves as an electrolyte in the corrosion process, and therefore its electrical resistance is one of the factors that affects the rate of corrosion. You would recall that in our discussion of corrosion in reinforced concrete structures, we had said that this is a reinforcing bar embedded in concrete, and at the time of corrosion, anodic sites are set up where iron goes to Fe2 plus and 2 electrons are released. Now, these 2 electrons, they travel towards cathodic areas through the reinforcement, but this movement of electrons is complemented by the movement of hydroxyl ions through the concrete, and that is what causes deposition of corrosion products at the anode. So, in this process, concrete is serving as the electrolyte. So, what's being stated here is exactly that, and if we are somehow able to control or estimate or understand the electrical resistivity of concrete, that is one way of controlling the rate of corrosion, because the rate of corrosion is basically directly related to this corrosion current. The fact that corrosion has happened or not happened is one story. The rate of corrosion, that is the instantaneous rate at which iron is being lost at the anode, is basically related to the corrosion current. So, if we are able to shut off the corrosion current, and measurement of the concrete resistivity is just one of those parameters that we try to understand as far as corrosion studies are concerned. And that's what's stated here, that measurement of the resistance or resistivity of the cover concrete is a common method used to study corrosion in concrete structures. Through resistivity mapping also, contours of equal values can be created and an interpretation made and appropriate action taken. So, much like the natural potentials in the previous slide, we have a concrete surface and we will be able to create contours of different resistivity values. Now, again, I am leaving it to you to find out more about the standards that deal with the measurement and interpretation of resistivity values as far as concrete structures is concerned. Coming to an end of our discussion as far as basic methods of non-destructive testing is concerned, what we have discussed is by no means an exhaustive or complete discussion, and only some of the common methods have been taken up. I leave it to you to find out more about other non-destructive testing techniques. Some of them were listed in the slides that we gave you, and some of them, of course, you can find out more through literature. Now, as we close this, I'd invite you to come with me to the laboratory and see some of the equipment that we often use and we have shown you in this lecture. So, continuing our discussion from the studio, let's try to come to the lab now and see how we collect data from the buildings as far as non-destructive testing and evaluation methods is concerned. So, we'll start with the Schmidt hammer. So, this is the Schmidt hammer, and we will see with the help of my colleagues how this is used to estimate or to get an idea about what the strength of concrete is. It's basically based on the principle of the hardness of the surface of concrete, as we have already talked about. We've talked about this in the class as well. It's probably a little difficult to see, but there are these calibration graphs which are given on each hammer, relate the rebound number that we get to the likely compressive strength of the concrete. Now, as far as the rebound number is concerned, there is a screen here which tells us the actual rebound number, and that rebound number is the average of a certain number of readings that we take, and that is what is given in our standards. So what we will see just now is a demonstration as to how these numbers are actually collected, and then what is the R value that it shows on the screen. So as you can see, as far as the structure is concerned, we need to mark out regions such as this at different points in the structure. And at each region, we have 9 or 15 or 17 or 20 points where we take the readings. And based on the readings that we get, there is a number which is displayed here, and that number is taken to this calibration graph, and that helps us estimate the strength of this concrete. Now, depending on different factors such as the fixity of this, the thickness of this concrete and so on, there can be a difference, and that is something which has to be borne in mind when we are trying to interpret results using the Schmidt hammer. And now we come to the estimation of strength using ultrasonic pulse velocity. So what we see here is the device that is used, and these are the two transducers which we use for transmitting and receiving the waves that pass through this concrete block. So in a direct method of measurement, the two sensors are fixed on opposite sides like this, or it could be on opposite sides like this. In indirect methods, when both sides are not accessible like this, we try to measure it in this fashion, or in this fashion as is marked here. So now we have a clear distance between these two transducers and the time it takes for the waves to travel from one sensor to the other. Based on that, we get the velocity of the pulse through this medium. What we will see now is a demonstration as to how these transducers are fixed and what kind of information is collected on this machine. So what we are seeing now is the application of grease to the concrete surface to ensure better contact between the sensors and the surface. So once we've done that, we have these sensors in the direct method, and what we'll see on the screen is the velocity as recorded. So in this case, we have already input the distance between the two sensors, and what we see is the time, which is 157.4 microseconds. So now that we know this time, we can calculate the velocity since we know the distance between these two sensors. Now we will see the indirect method of measurement using the same concrete. So what we did previously was the direct method of measurement when the two transducers were opposite to each other. Now in this case, they are on the same face of the concrete, and we can see that the time is 59.7 microseconds. Now the distance we can find out, we can measure between the two sensors. We have talked about core extraction. So this is a portable core cutting machine, and as you can see, we need to fix this part to the structure where we want to take the cores out of, and this is the drill bit. So depending on the diameter of this bit, we can get a core which could be, let's say, 75, 77 millimeters in diameter, or we can get a core which could be, let's say, about 50, 55 in diameter. So now it depends on us how we are going to use this core. And that was an assignment which had been given that, okay, what is the kind of information that we can extract once we get this core from the structure? It had also been pointed out that it's not a very good idea to take many cores out of the structure, especially when it comes to evaluation. We would like to take samples at different points in time, and that no owner of a concrete facility would allow extraction of multiple cores at multiple times. So this is something which has to be resorted to very sparingly. What we have to also ensure that we do not cut the reinforcing bars like this. Number one, that is detrimental to the structure, and number two, it's also very detrimental to the health or to the integrity of the drill bit. So we must avoid having to cut through reinforcement. Now, how we avoid doing that is using a cover meter or some kind of a survey by which we should know where exactly are the reinforcement bars located. That's something which I'll show you in a demonstration just now. Now coming to the problem of locating a reinforcing bar behind the surface of concrete. Now this in my hand is a portable cover meter or a rebar locator, a device that tells you how deep is the reinforcing bar from the surface, that is the cover, and the rebar locator, where exactly the bar is. Now we'll see how the device works. So if you look closely at the screen, there is a reading which says infinity. That is, a reinforcing bar is very far from the surface of the locator. So if we take it close to a surface, this reading is exactly what's going to tell us how deep is the embedment. So with the help of my colleague, I'll show you how the rebar locator is actually used. So as we move the rebar locator along the surface of the reinforced concrete structure, we can see the reading on the right change to different numbers. For example, now the reading is 31. That is, the reinforcing bar is 31 millimeters from the surface. At this point, the reading is also 31, showing that this reinforcing bar is also at 31 millimeters from the surface. If you read it in the middle, the numbers will be much larger. So for example, here it's giving you a number of 51. Now this 51 is exactly what we have to be very careful about. So because this is a lab sample and we can see that there is no reinforcing bar under this locator, but the reading 51 is basically some kind of a number which is being displayed. So while we are carrying out this survey, we have to be careful in interpreting the numbers that we get from the locator or from the cover meter. Also, device manufacturers sometimes claim that this device can be used to measure or estimate the diameter of the bars that are there. So for example, in this case, the diameter that the locator is showing is something like 11 to 12 mm. That is something which is being seen on the left hand side of the screen. So now it requires engineering judgment to be able to say that yes, the diameter of the bar is likely to be 12 mm. Because as engineers, we know that there are no bars which are available having a diameter of 11 millimeters. So at this location, the diameter which is being estimated by the device is 16 to 18 millimeters. Again, engineering judgment tells us that the bar is likely to be 16 mm in diameter. Now this is another device, the ground penetrating radar, which is used to scan the concrete surface and find out the location of the reinforcing bars. So as we can see, the reinforcing bars are located 31 or 29 millimeters from the surface, and there are 4 bars as you can see. So in an actual structure, we do not know how many bars are there. So what we do is carry out this scanning in both directions and get a map of the likely locations of the reinforcing bars in both directions. So after processing the data that is collected through the scans, we get an image which is something like this. So this shows us the location of the bars in the 2 directions. That helps us identify a location such as this or this to take cores without having the fear of cutting the reinforcing bars. We've talked about measurement of crack width in concrete. Now suppose we had a crack which was something like this, the line shown here. We use this device, which is a crack microscope, put it across the crack, and then through this eyepiece we can see and find out what is the width of this crack at different locations. So we have to keep moving this and we can record the width at different locations. So we've talked about measurement of carbonation depth. Now in this core, we can see the depth of carbonation as recorded at different locations. So this core has been extracted from a structure, and using phenolphthalein, we find that this part has the pink coloration and this part does not. So we have this kind of a variation which we can see as far as the carbonation depth at different locations is concerned. So with this, we complete our demonstration for the day. We've seen different equipment, how they are used to estimate the crack width, the strength of concrete, and location of reinforcing bars and so on. As we can see, it's a very cumbersome exercise to carry out any of these investigations. And that is something which, as infrastructure managers, we must keep in mind when we plan non-destructive testing and evaluation procedures in actual structures. So with this, we go back to our studio and continue our discussion as far as the lecture is concerned. So let's move on from what we saw in the laboratory. As mentioned in the lab also, I hope an exposure to some of those equipments and some of the specimens that we use was helpful to you in understanding at least the limitation of it in terms of how those small equipment can be used to evaluate a large structure. So in summary, as far as our discussion today and the previous discussion when we talked about the other non-destructive methods such as the Schmidt-Hammer is concerned, it was more directed to create a sensitivity and awareness towards non-destructive testing, to understand that NDT investigation requires resources and planning, and the methods have their own limitations. We have to be very careful in making interpretations, and that has to be carried out in the context of the specific investigation being done. It's very easy to draw a graph like this, which talks about deterioration going like this and performance going down with time, trying to define service life here and saying that, well, the design service life and the critical deterioration value, all this is very good. But when it comes to actual practice, this is easier said than done. We have so many methods to get information about specific parameters, whether it was the strength of concrete, whether it was cracking in concrete, whether it is the natural potential, and so on and so forth. It requires engineering judgment to be able to come up with a specific index that can be related to performance or that can be related to deterioration. We can get natural potentials, yes, but natural potentials, are they the only way of defining deterioration? Perhaps not. As far as corrosion studies are concerned, apart from natural potentials, you will also find other methods which give you a lot of other parameters. And then, as an engineer or as a manager of an asset, we have to be careful in choosing the methods which are reliable and give us the kind of information we need to be able to find our location on this curve, whether it is deterioration or whether it is performance. And that is what we had alluded to when we said that there are deterioration parameters and there are performance parameters. Yes, there is a relationship between these two, but it's something which needs to be explored and established as far as different infrastructure are concerned. So with this, we close our discussion on non-destructive testing and evaluation as far as concrete structures is concerned. And it's hoped that with this illustrative example, you are in a better position to understand the limitations and the range of application, both sides, of non-destructive testing and evaluation of different structures. Before we close, I'll leave you with some food for thought. Make a list of available methods to quantitatively understand the reinforcement corrosion in concrete. Study the details of the natural potential and resistivity measurements. Find out more about the specific interpretation in terms of results from these methods. Make a list of available Indian and international standards relating to the test discussed, not necessarily only the natural potentials, but also perhaps Schmidt-Hammer, ultrasonic pulse velocity, and so on. Make a more in-depth study of applications of infrared thermography to structural health monitoring, and understand how the course of the structure can be used to get more information about the state of concrete in the structure. This is something which I had also mentioned to you before we went to the lab, and said that course can be an invaluable source of information, but the number of course that can be taken is very limited, and therefore we should try to extract as much information as possible from core samples. And here is a list of suggested reading and reference material that could be useful to you to understand the discussion that we've had today. And as usual, before I close, I would like to thank all my colleagues, teachers and students over the last several decades who have helped me understand this whole profession of non-destructive testing, deterioration and infrastructure management better over the last decades. Thank you.